Okay, here I take a look at three separate back titrations, otherwise known as indirect titrations. In each of these cases, in general terms, I'll take a chemical A of unknown concentration, and to make sure it completely reacts, I'll react it with an excess of a chemical B to form products. In each case it'll be a neutralization reaction, this A plus B reaction. If A is a base, then B will be an acid, or vice versa. Now, where do we use back titrations? Well, in several different scenarios. Where, for example, the chemical A is insoluble, either an insoluble acid or insoluble base. Examples of an insoluble base commonly used in these questions, such as magnesium oxide or calcium carbonate, which might be present in chalk or limestone, for example. Another example might be where you have a chemical that is volatile, such as ammonia dissolved in a domestic cleaner. So if you were to compare the concentrations of ammonia in different domestic cleaners, what you really want to find out is the concentration of the ammonia in the solution when you remove it from a freshly opened bottle. Now, during the course of a normal titration, the ammonia will be escaping from the cleaner, so it won't work. You'll see shortly how back titration overcomes that problem. And then there's also a scenario where the chemical A reacts with the titrant from the burette too slowly, and again a back titration is best in this case. Back then to the separate steps of a back titration. In step 1, you add a so-called known excess of chemical B to make sure that all of A reacts, and you work out how many moles of B you've added simply from the volume and concentration that you've added. In step 2, you carry out a back titration, an acid-alkali or acid-base titration, to determine how many moles of B is left over. In step 3 then, a subtraction. If you take the number of moles of B left from the moles of B added, you'll get the number of moles of B reacted or used, and from that, in step 4, you'll be able to work back and determine how many moles of A must have been present. So those are the steps. Here's an analogy or comparison that might help you to understand the general principle of a back titration. I need some milk, but I don't know the price of the milk. So I send my son to the shop and I give him more than enough, £20. In chemical terms, this is referred to as the known excess. So he returns with the milk and my change. My change amounts to £19.20. So how much did the milk cost? So I sent him with £20, the change £19.20, and so I'm able to work out that the milk cost 80 pence. And this is the general principle, as you'll see, I hope, of the three back titrations that come up here. Let me take this analogy and superimpose it on the writing frame that I'm going to use for the three back titrations that follow. So £20 was the amount sent, a known excess, the change £19.20, the difference in those, the cost of the milk. That'll be my writing frame. In these back titrations, by the way, there are always three chemicals. Using a pipette, you'll add the known excess B, but in addition to A and B, you'll have a titrant as well. If A is a base, B will be an acid to neutralize it, and to determine the number of moles of B left, the titrant will be a base. Okay, let's take a quick overview of the back titration technique. Let's say we had magnesium oxide to be A, then hydrochloric acid would be suitable for B, and the titrant sodium hydroxide might be used. First, we use a bulb pipette to add a known excess of hydrochloric acid to the magnesium oxide. So we have an acid-base reaction. Should form soluble magnesium chloride in water. Using N equals CV, we work out the number of moles of this known excess of hydrochloric acid. Remember to change the cubic centimeters to cubic decimeters. That's the value V in the expression N equals CV. So there we've got 0.025 moles of B, a known excess added to the magnesium oxide. We now work out the number of moles of hydrochloric acid left over using a titration with sodium hydroxide. Let's say the average titer was 10 milliliters or 10 cubic centimeters. Again, we'd use N equals CV to determine the number of moles of sodium hydroxide dispensed from the burette. In this case, 0.005. Look at the equation between HCl and NaOH. They react in the ratio 1 mole to 1 mole. So that tells us there must have been the same number of moles of HCl remaining in the conical flask. So next we subtract the number of moles left from the number of moles added. There you are, and we get 0.02 moles of B must have been used to react with the magnesium oxide. So lastly, we need to take a look at the balanced equation for the reaction of magnesium oxide with hydrochloric acid. To balance that equation, we needed 2 there, so they react in the ratio 1 mole of MgO to 2 moles of HCl. So the number of moles of MgO will be half the number of moles of HCl, hence 0.01. And there you have it, the 5 basic steps in a back titration. Just pause and have a look at these before you start the actual questions. So pause here and take down the details of this first of 3 back titrations that we're going to look at. It involves magnesium oxides that's only slightly soluble in water, so it's our chemical A, so to speak. And we have 4.06 grams of an impure sample of magnesium oxide. Chemical B, the one that we refer to as known excess, 100 cubic centimeters of 2 molar or 2 mole per cubic decimeter HCl. And the titrant, sodium hydroxide, 19.70 cubic centimeters is the average titer, concentration 0.200 mole per cubic decimeter. I'll stick with this writing frame to get you used to the basic steps of a back titration. So let's take a look at chemical B, which in this case the known excess is 100 cubic centimeters of 2 molar HCl. So we use N equals CV. That's 2 times 0.1. Remember to change cubic centimeters to cubic decimeters there. So the number of moles, 0.2 moles of B. B being hydrochloric acid, of course. So you take a bulb pipette. Here you see a 25 milliliter or 25 cubic centimeter bulb pipette. This question would require you use a 100 cubic centimeter bulb pipette. Next we work out the number of moles of HCl left over. The average titer 19.7 cubic centimeters of 0.2 molar sodium hydroxide. We work out the number of moles of NaOH dispensed. There it is, 0.00394 mole. We need to take a look at the balanced equation between NaOH and HCl. And you see here that they react in the ratio 1 mole of HCl to 1 mole of NaOH. That means we must have had the same number of moles, 0.00394 moles of HCl in the flask. That's the number of moles of HCl left. So if we subtract the number of moles left from the number of moles added, there you have it, we get 0.196 moles of HCl must have reacted with the magnesium oxide. Next we take a look at the reacting moles between MgO and HCl. And you see from the balanced equation that 1 mole of MgO reacts with 2 moles of HCl. That means we must have had half as many moles of MgO present in the sample. That's 0.098 moles of MgO. What mass would that be? Well, we need to work out the formula mass of MgO. That's 24 and 16. Formula mass then is 40. To work out the mass in that number of moles, we multiply the number of moles by the formula mass. And there you have it, 3.92 grams of MgO in that sample. The sample having a total mass of 4.06. And there you have it, there's the percentage purity of the sample, 96.6%. If that was too fast, then I suggest you pause and review the 5 basic steps here. Right, pause again and review this question. So here we work out the percentage of calcium carbonate in a sample of chalk. So this time A is going to be calcium carbonate. We have the mass there, 0.125 grams. And we're using hydrochloric acid again as B. And the titrant is sodium hydroxide once again. So pause, take down the key figures that you need. And here's the writing frame once again. So pause and give it a good go. First step, to work out the number of moles of the known excess of hydrochloric acid. N equals CV, so 0.2 times 0.05 gives us 0.01 mole of HCl. That's the number of moles of HCl added. Again, the titrant is sodium hydroxide, this time concentration 0.25 molar. And again, we use N equals CV to work out the number of moles of sodium hydroxide dispensed from the burette. turns out to be 0.00803 moles. Then we need to take a look at the equation between sodium hydroxide and HCl, and we see here that they react in the ratio 1 mole to 1 mole. Therefore, the number of moles of HCl remaining in the flask is the same as the number of moles of sodium hydroxide dispensed from the burette, 0.00803 moles. So we subtract the number of moles of HCl left from the number of moles of HCl added. There you have it. The difference is the number of moles of HCl used to react with calcium carbonate, 0.00197 moles. Next, we take a look at the balanced equation for the reaction of calcium carbonate, chemical A, with hydrochloric acid, chemical B. And they react in the ratio 1 mole of calcium carbonate to 2 moles of hydrochloric acid. That means the number of moles of calcium carbonate is half the number of moles of HCl used up. And that turns out to be 0.000985 moles of calcium carbonate. Let's work out what mass that would be. First, we need to get the formula mass of calcium carbonate. Turns out to be 100, as you see there. So if we multiply the moles by the formula mass, we'll get the mass of calcium carbonate in that sample. Turns out to be 0.0985 grams of calcium carbonate. Lastly, then, we can work out the percentage of calcium carbonate in the chalk. There you see it's 0.0985 over the mass of the chalk, 0.125 times 100%. And here's the last of the 3 questions. Pause and give it a go. Pick up all the facts and figures. A is ammonia in this case. Ammonia is a volatile substance. If it's present in a domestic cleaner, when the cleaner is poured out into a beaker, the ammonia will begin to escape into the atmosphere. So during the course of a titration, the concentration will be changing, hence a back titration is necessary. So A is ammonia, B is hydrochloric acid, and the titrant this time is sodium carbonate. You'll see here again on the writing frame, I've summarized the facts and figures, so pause and give it a go. So we use N equals CV to work out the number of moles of the known excess, this time 50 cubic centimeters of 0.100 molar HCl. Turns out to be 0.005 moles of HCl. Look at the sodium carbonate, 0.05 molar, and the average titer 21.50 milliliters or cubic centimeters. Using N equals CV, we determine that 0.001075 moles of sodium carbonate has been dispensed from the burette. Then we take a look at the balanced equation for the reaction between sodium carbonate, the titrant, and hydrochloric acid in the flask. They react in the ratio 1 mole to 2 moles. So the number of moles of HCl in the flask will be twice the number of moles of sodium carbonate dispensed from the burette, hence 0.00215 moles of HCl. Then we subtract the number of moles of HCl left from the number of moles of HCl added to get the number of moles of HCl used. There it is, 0.00285 moles of HCl. Next, we consider the reaction of ammonia, chemical A, with HCl, chemical B, and you see there they react in the ratio 1 mole to 1 mole. So the number of moles of NH3 that was present is the same as the number of moles of HCl used or reacted, 0.00285 moles. But we were asked to work out the concentration of the ammonia. This time we want C, not N, so we rearrange the expression N equals CV to get C equals N over V. Put the values in, and there you have it, 0.0114 mole per cubic decimeter ammonia.